the record. Oh my god. Okay, so this is the re method 2. Using the radius of curvature, and we got these velocities for v, for v1, v2, and on. And here we got a nice relation of r and theta. So okay, but for that the angle r plus. And do we have some relation with this angle and theta? If I see, reflection property is okay. I'm getting something now. So from the angle bisector property, I think the ratio of the sides will be in the ratio of this side, no? Some relation, something like that exists. I think.
Uh, sir, like OP by, sir, like the ratios of the sides,
Yeah,
OP by PC is equal to the position of that
yeah, A over by
A
AC.
by AC.
I think something like that exists, no? Angle bisector relation. I think something like that we can have. Um, yeah, that should be, I think. So that makes sense also. Angle bisector theorem. Okay, let me just search what is, I just forgot this. Yeah, exactly. That's the relation.
Yes, sir.
Yeah, that's easy to prove also. I don't know why. Okay, anyway. So angle bisector theorem says that this ratio will be same. So R upon 2A minus R will be equals to OP upon PC, right?
Yes, sir.
And we know that OP plus PC is how much?
It's equal to AE.
Ah, yeah, right. And because we know the ratio, so OP equals to how much? It is the r upon 2a of this, right?
Yes, sir.
Yeah, so that's very interesting. So OP is, oh nice, ER. Cool. Yeah. So PC is how much? This will be the difference.
So I don't understand the third statement that you wrote, sir. 2AE into.
The sum is given, the ratio is given. How to find the fraction? This will be this upon sum of the fraction into this length.
Yes, sir. Yes.
Or do one thing. You can solve this separate. Let's remove from here. Next week. Go to. Okay, I will do this. Today I am on a mission. I have thought of exploring writer. So what I'm saying is that SP upon PS dash must equals to R upon 2A minus R,
Yes, sir.
and SP plus PS dash is how much? 2A. So can you solve these two questions and tell me the SP and PS? But can I write SP equals to the R fraction of 2A, where the sum is 2A, na? If you add these two fractions, you get 2A. Into the separation, the 2A, correct? Do you realize this? No, I think
Yes,
you're
sir.
not. You realize? Exactly.
So like taking the reciprocal of it and adding one and
Easily,
doing
I
it.
can,
Yes, sir.
if you just solve these two questions, you get the same answer. This is what I'm saying. You can check for yourself that solution of this will give you this answer. So SP turns out to be ER. That is what I'm saying.
Yes, sir. I got it, sir.
And if SP is TR, then PS dash will be how much? It's 2AE minus ER, correct?
Yes, sir.
So PS dash turns out to be what I can take common E. So it's E times of this value. It's like the E of this side is this length. It's again a very interesting relation which we just discovered, that this
Yes,
will
sir.
be exactly E times R, and this will be exactly E times the distance of this side, 2A minus R. Do you realize this?
Yes, sir.
Okay. 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 Hmm. Hmm. So this angle, uh, if I try to prove that alpha equals to alpha, so I think that is kind of self-evident now. Something really interesting happened. Okay, so now we have to find the radius of curvature. I think we have taken a very tough task to finding the radius curvature of any random point on ellipse. Uh, that we can
Yes.
that we can leave it. I mean, this part is not we should think about. But what anyway, we came across something really interesting that R and 2m minus R and then the bisector relation is exactly the same.
Yes, sir.
Okay. What else we can do from this ellipse question? So if V is given, then we can do something. So if V is known to us, okay. Because what we need is this angle. We need, so we know this angle is going to be 90 minus alpha. So this will be 90. This is going to be alpha, right? Yeah, that is any alpha. Why I'm doing this? So the angular momentum about S will be how much? M VR sine 90 plus alpha, right? The angle between the V vector and R vector.
Yes, sir.
So the angular momentum turns out to be MV and 90 plus alpha is cos, so R cos alpha. And R cos alpha will be how much? The vertical height. No. This R cos alpha will be some new value. So again, I need to find cos alpha. Okay, I was looking for theta relation. Like what is the relationship between theta and alpha? So we can find cos alpha. Cos alpha will be equals to, or no, even I don't know the middle term. But we can find that. Yeah. Okay. I got it now. Cos 2 alpha equals to R square plus minus upon minus R. Yeah. I think I should stop now. It's getting too much, isn't it? Yeah, this is now okay. It's not going to be solved. I'm trying to discover some mathematics actually. Anyway, so okay, I came to know something really interesting, which I'm proud of. Anyway, so I got to know that in ellipse, these are the very interesting relations. That once you know the R, the ratio will be exactly ER, and that
Yes,
itself is a really interesting. So it may help you in mathematics. I don't know. And the reflection property is also something you should be aware of. That in ellipse, the tangent and the normal will divide the angle into equal values because it follows the laws of reflection. So if the light ray will emerge from here, it will come to this point. If you keep an object here and if you make the ellipse as a mirror, the reflection will bring the light ray back to the next focus. So light ray from the first focus always goes to the next focus. That's the rule of conic section. Okay.
So for the whole of conic sections?
Yeah, whole. Let's say if you have a parabola. So let's say if you have a circle. So any light which will leave the center will come back to center.
Yes, sir.
Because the center itself is the next focus. Both focus are same. Na?
Yes, sir.
If you have a parabola, so we have one focus here, other at infinity. So if the light ray will leave here, it will become parallel.
Yes, sir.
And that is why we use the parabolic reflector in the headlamp. We don't use the spherical. Now you know why.
Yes, sir.
Because the light will go to the infinity, so it will have the maximum range. Okay. So
Yes, sir.
we use parabolic reflector. We don't use circular or spherical reflector.
Okay, sir.
Okay. Just a moment. Let me see something about orbits. I wanted to do something about this today. Yeah, just okay, so complete theory itself. Oh, nice. Just- Ah, now I remember. So we have to express the answer in terms of semi-lattice rectum. Yeah, because semi-lattice rectum is also very famous term. Anyway, so it's my done. Okay, I'm done with my experiment. So what you are supposed to do is you're supposed to solve question from the E row dove. Okay, and you start with 1.200. So today in the whole lecture, the lecture is I'm not going to teach today anything, but you are supposed to go through Irodov, and if doubts come, then I will solve. So start with 1.200, and we have just 33 questions. So today you should solve at least 10 questions.
Okay, sir.
So I'll just mark it. So you start with the first question, and it's better to solve alternative question, like alternate 10 questions, so that you can cover maximum part.
Yes, sir.
Yeah. So start now. Okay, that's easy only. So you have to use these formulas. Mostly Kepler's law questions are very much given in the Irodov. So that's why Irodov is good for practicing Kepler's law.
Sir, most of the questions here are of Kepler's law, sir.
Yeah, yeah. Gravitation means Kepler's law only, because the rest of the gravitation is electrostatics.
Yes, sir.
So let's say if I give you the distance of Pluto, you can find the time period of Pluto, how much time it will take. Because you know the distance of Earth and you know the time period of Earth. This is 365 days.
Yes, sir.
Okay. All right. Right. How many you solved, Hasika? Tell me.
Sir, I'm solving 203 right now, sir.
Okay, great. So you got the first two questions.
Yes. So the first three, sir.
First three, great, great. Oh yeah, two, one, one, two.
Sir, I'm not exactly getting an idea for the third, I mean like 203, sir.
Just a minute. 213, na? Two.
Sir, 203. Sir,
Yeah.
203.
Just. Ah, that's interesting question. So if you remember, I told you that even everything is ellipse, and if I make the eccentricity infinite, it becomes pair of the straight line, right?
Yes, sir.
So imagine that this is sun, and this is the center of sun, and something is moving around the sun in a orbit of Earth, which means the distance of the Earth from the sun is how much?
Sir, I don't know the exact value.
It's one astronomical unit, which is equals to 1.5 into 10 power 11 meters. Okay,
Okay, sir.
it's very easy to remember. How to remember? I have told you. No? The light from the sun takes 500 seconds to reach Earth,
Yes, sir.
and the speed of light is 3 into 10 power 8 meter per second.
So we can multiply the two.
Yeah, the distance
Okay.
is that's why. So this is the roughly, I mean, not the exact answer. So we know 8 minutes and 48 seconds, right? Something like 48 seconds. So 8 minutes is how much?
480.
480 seconds, and you can add like it's more than that. But we take the 500 as a rough calculation, and that's easy. Also, this is the mean distance because some distance is the Earth and sun distance is not constant, right?
Yes, sir.
So that's called the mean distance, and that's how we remember. Okay.
Okay,
So
sir.
now, if you move around the sun in the orbit, and if I choose the orbit to be circular, the time period is we know 365 days. Okay. If I make the velocity of the object zero, the gravity of the sun will start pulling it towards its center, right?
Yes, sir.
So in such scenario, what will happen? It will directly fall towards the sun.
Yes, sir.
This we can approximate by this relation. So we can assume this is like the flattest ellipse around the sun center. And the point of projection, we talk about this as the apogee. So this will be like the semi-major axis because we are supposed to find the a rough estimate. So we can treat this ellipse as the semi-major axis. This becomes 2a. Okay, and we can
Okay.
call this as, so we can call this is ellipse of major axis
Sir, isn't the
A.
sun supposed to be at the focus?
Yeah, so the focus is almost touching the center. Okay, so this is how we assume that the ellipse is having the foci. So as you make it thinner, the focus will shift towards edge, right?
Yes, sir.
So at the circle center is the focus, and now focus is shifting away, 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 away. So in the worst case, the focus will be at edge only. Understood?
Yes, sir.
So you can imagine this is the focus, which is also the center of sun. Anyway, so the way to understand is that for any elliptical motion, this journey we can treat as half ellipse traveling towards the sun, right?
Yes, sir.
And compared to the distance between the earth and the sun, we can treat sun as a point mass.
Yes, sir.
So it is like you have to reach it. How much time it will take, or this planet will take to reach here, is actually traveling half of the ellipse.
Yes, sir.
And because focus is exactly at the edge, so time taken to go from here to here will be the half of the time period, right?
Yes, sir.
So we can call this time period if the ellipse. So what is that? If I call the t as the time period of the flat ellipse, then the square of the time period will be proportional to what? The cube of the same image axis, which is like a.
Yes.
And if I talk about the actual path of the satellite moving around the sun, so their path will be equals to the 2a whole cube, because that's like a radius. This is the earth. Can we say that?
Yes, sir.
So what we can say that the t flat ellipse, okay, let's make a tf, I don't know to. So this upon t earth square is 1 upon 8, right?
Yes, sir.
So t flat is how much?
It's by 2 root 2.
2 root 2. Yeah, correct. But the time taken will be half of this, no?
Yes, sir.
So the time taken to fall on the earth, because we are just falling, we're not completing the ellipse. So that will be equals to roughly equals to tf by 2.
Yes, sir.
And therefore this will become t earth, the time period of earth by 4 root 2. I need to check the answer. I don't know this. 1.203. Yeah, that's correct answer. 1 by 4 root 2 is the right answer. Yes, yes. You can see the answer was given in the Erodom only, so even we learned from their own. So even I was not aware of this concept, to be honest. So I read this answer, then I came to know, okay, this is a concept of ellipse in this fashion. Okay. Is this clear?
Yes, sir.
Okay, I'll teach something before I proceed with the new question. So the concept is, yeah, this I should have explained, which I missed. So equation of, sorry, path of trajectory. Path of trajectory. So let's say if you think any planet, let's say we talk about the Earth, or you can choose any planet, Sun also. Okay. So if this is the planet, and if I project something from a certain height, with some velocity v, then based on the velocity, there are many possibilities. So the object may fall back to Earth, right? Quite possible.
Yes, sir.
The object may start moving in a circle. Now, moving in a circle does not mean you're trying to move in a circle. You're trying to fall, but you fail to reach the earth. So you always keep on turning, but you never come to the earth, right? That's called falling. So when a satellite is moving around the planet, this is a free fall actually. Understand? Do you realize this? This is free
Yes, sir.
because you're turning towards the earth, but you're not coming exactly here. Okay, so this path is also the okay. I'll come to that. If you throw even faster, it will start going this way.
Sir, and then will it be like joining in orbit of different
Yeah.
radiuses?
So it will move in a big ellipse, a bigger ellipse. Okay, I can draw this separately. So there are a variety of paths which I can draw. So a small ellipse, then a big circle. Then next comes is called the big ellipse. And then after that, what will come is the parabola and hyperbola. That's the last kind of motion. So I will remove this. So you cannot really differentiate because these are mathematical differentiation. But what we call parabola or what we call hyperbola, they are having mathematical differences. Okay. So there's nothing like a difference in terms of physics.
Sir,
Yeah.
sir, why does why do the planets move in an elliptical path around the sun, sir?
Because see, what happens? Let's say if you throw something very fast, so if you do not throw with a speed which is equal to the orbital velocity, because we have seen that every orbit will have the predefined velocity, right?
Yes, sir.
I mean to say every circular orbit will have the predefined velocity. So what happens if you throw with the velocity faster than the orbital but less than the escape? So you are still trapped in the gravity of the planet. So it is like free falling, but you never come back. Imagine. So you come very close, but you always, I mean, it's like because of the inertia, you go some other direction.
Oh, okay, sir.
So what exactly happens is, let's say if I let me complete this part, this is, I will consider as so we, as I said, every bound system will have some energy constraint actually. So if I dug a hole around the earth, the object will keep on moving like this forever. Okay, so if you throw something not very fast, it will fall back on the earth, and the height from which you throw, which is the earth radius, the RE, so the first case is case one. If the velocity of projection is less than orbital or the first cosmic velocity, if you remember, in that case, every object will fall back on earth. Okay. So if you throw something with velocity less than this, it will exactly fall back to the earth. Wherever it can flow, like it can fall here also, it can fall here also, it can fall, but it will fall eventually back on the earth. So that's the path will be elliptical path. It's not like as you solve in the projectile motion, you call it parabola, right?
Yes, sir.
So we can't say this is parabola. You know why?
So because, sir, is there any condition on this height like it's comparable to the Earth's radius?
It could, yeah, the h is in general, so it could be any height, any height, like bigger height.
Sir, that means the G value will be varying, so because of that.
Yeah, correct. So the parabolic path is only possible under the uniform field of gravitation or other field. So
Yes,
whenever the field is uniform, then only path is parabola. So for if I consider it a general height in which the field can vary, then and that's why you can also understand that a parabola and the ellipse are a very special case, right? So the moment the variation will stop, if the field becomes uniform, the path will change from ellipse to parabola, isn't it?
yes, sir.
So when this is the case, then we say it is a parabola. And what else we need to understand that the height at which you project the height at which you project this becomes the perigee, the farthest point from the Earth. Because anyway will come closer, no? So this is the farthest point from the Earth.
Yes, sir.
This is the this is called the apogee. What I'm saying, the farthest is called apogee, or basically it's called apohelion. Apohelion, but it is not helium. So we in general we call it epis. I mean, maybe you can say epis means the farthest point. Understood? Just a minute. Just give me 2 minutes, okay? I'm coming back. Yeah, hello. So this is the first case. Epis means the farthest point. So in this case, how to solve the question? Let's say if the height is h and if the radius is re, the Earth radius, then the semi-major axis will be how much? Re plus h. Understood?
Yes, sir. Yes.
And this is the major axis, and the focus we take the Earth center in such. So we take the Earth center as the foci, and that is why the journey will be simple. You have to travel half here and half this side. Okay.
Yes, sir.
Also, because the time period is proportional to the area covered, so half journey means when you have swept the half area, you will also take half the time period. Understood?
Yes, sir.
Okay. So what happens when, let's say, a planet is moving any satellite? Let's say we talk about the man-made satellite. So you launch something in the space. Okay. So let's say from Earth we launch a satellite which makes the orbital motion around the Earth. Okay. Now, because of some failure, we need to bring it back on the Earth. Okay. So what we do is we try to stop it. Sometimes in the space we have so many explosion that the debris which we spread by virtue of explosion is also creating some sort of pollution which we call cosmic dust. So the entire universe is filled with cosmic dust of one form or the other, because many a times, the stars are, kind of exploded into tiny pieces, which we call supernova. So the space is full of debris. So we have comets also, which is nothing but a debris only. And the comets will have the long tail. So when we have a comet, it will have a long tail, and the flame from the comet will kind of start freezing down, and they create the tail-like shape. So tails are basically the cooler part, and the actual part is the bigger part is the fusion part, where the heat is liberated. Anyway, so when comet passes near the, let's say, Earth's atmosphere, the cooler part will actually freeze it, and you can see the tail of comet. That's how the comets are inspected in space, as a star with a long tail. Anyway, so what I'm saying is, let's say if a satellite has to bring it down, so what we do is we generally bring the satellite down in the some ocean, Pacific, or whatever is near the orbiting station. So what we do is we make the velocity of the satellite to be zero, and we make sure that it should not fall in the vegetation area, but where the people live. So what we do is we first make the velocity zero, and once you make it zero, it will free fall, and you can choose that, or you can imagine that path as the uh, elliptical path. All right, and it will fall back, and then you can actually find the time period. So let's say any orbiting satellite, we have seen that it takes 1.4 hours to complete the circle, right? If you remember.
Yes.
So the orbital motion is 1.4 hours. So how much time it will take to fall on the Earth? Can you calculate? Imagine.
0.7.
So the height of the orbit for the motion that we consider is very small. It's a small h. So if I take h in general, h plus re, then the time to fall, let's call it small t. So that double the time to fall. Uh, 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 then this is like, of course, in a difficult situation, we have to take one particular case, then we can solve. Okay. So of course I will not.
H greater than RE, like.
Yeah. I'm considering much bigger than R. So, or maybe I can take as R. So I can take some other satellites, at a really good height. So what I'll do is I'll finish this part, and then I'll come back to the question actually, because I'm trying to create a question which you can solve. Okay, so this is the idea. What is the idea? The point at which you throw will become I mean, not G, I can change by something like, if I change this as Earth as Sun, then it is good to say apogee. But anyway, I can choose the apogee word here also. The idea of apogee means not only Sun context, you can use for any planet. Now it's like just a very common terminology. And apogee means the farthest point. Clear?
Yes.
So this is what you can say in the apogee part. Now, if we come back to the other part, let's say the perigee part. Okay, sorry, this is the first part. So this is something which you need to understand or remember. The next concept is, so now the next concept is simple. If V is equals to VO, the path will be circular. That's it. So the orbit is going to be circular, and what you need to remember that in all case except the when you exceed the escape, or equals to escape, every velocity less than escape is called free fall. You must realize this. So anything which is moving around the sun is actually not moving around. It is getting attracted towards the planet or the sun, but they never reach it. That's why you see it's moving always. Understood?
Yes, sir.
That's very interesting. Do you realize this? Like why everything is moving? Look at
Because it
this.
is influenced under some other
Yeah. So see, if you throw
acceleration
something,
body.
if you throw something like this, it will fall like this. If you throw faster, it will try to fall like this.
Yes, sir.
If you throw really fast, then it will never come back because it is trying to come towards the earth. But while doing so, it will move like here, then here. So it will maintain the distance always. So you are trying to come closer, but you are turning by the time because of the inertia, and therefore the gravity is only able to turn but not bring it back. Do you realize this?
Yes, sir.
That's why this is the, you call it circular path. Okay, so you can think this way, like the way Newton thought that a moon is, if you talk about the moon, so let's say we have the moon somewhere here. After some time, the moon has fallen down. It is here. If you think in terms of falling down, you can see that you can see it has come down by this value, right? But while coming down, the velocity has also taken it forward. That is the problem that you never see coming closer. So these are free fall actually. Do you realize this? These are free fall.
Yes, sir.
So again, further, if you look from this side, and if the planet goes here, you have come down by this value. Do you realize this? Again. But while coming down, while coming towards the Earth, you have gone away also. Inertia. And that is how you maintain the distance from the planet, and that's why we call it freely falling. So every satellite, every natural or man-made satellites are actually freely falling around the planet. Understood?
Yes, sir.
If you give some extra velocity, then it will try to fall in a very different way, like it will come back. So it will go far away, far away, far away, far away, but it will never fall back on the planet. So paths can be either elliptical by definition or circular. Now, if you throw at a speed called escape, what is the meaning of escape? You leave the gravitation of that planet in which was governing your motion. And when you escape, it means you go to the influence of the next big planet or star. So when something leaves the Earth, where it goes? It goes in the gravitation of sun. So it is like I'm throwing a ball, okay, and you catch it back. When I say you catch it, it means, so imagine if I talk in terms of the space curve, this is like a blanket or some sheet which you have hold like this. So if you throw something, it will fall back. There is another blanket in the nearby universe part. So if you throw really fast, it will fall back here, and if you drop, it will go like this. It will oscillate like this.
What is this
In
blanket?
a way, yeah.
Sir, what
But
is this blanket?
it is like a space blanket. Imagine a big space blanket in which you have a object. So if you throw something, or not like this, not from top. Imagine that you okay. Imagine you have another blanket. Blankets are like a curved part, right? So every planet, if this is a planet, the space around the planet is like a curve.
Oh, yes, sir.
It's like a three-dimensional curve. You can see if you hold a blanket from or any bed sheet from two sides, you must have seen there's a curvature at the center.
Yes, sir.
And if you drop something, it will move around this curvature, right? Like a membrane.
Yes, sir.
So what Einstein said that every planet around its vicinity creates some sort of trench like this. So this is like a curve. If you drop something here, the planet will try to fall like this. But if you give some velocity, it will turn like this. If v will decrease, it will go like this, spiral, and it may come out. What I'm saying is, escape velocity is a concept in which actually you leave this blanket and fall on the other's blanket. Now here, if I release, it will go here. It will go towards this planet. Understood?
Yes, sir.
So it is like the entire universe is filled with blankets, and all blanket is representing the space-time curve in which the localized center is the governing planet. So in a small blanket, this is the first blanket. Let's imagine this is a small blanket of Earth. So Earth is able to create, let's say Earth is able to create this kind of curvature. So if I look at the bigger picture, then the sun is having the biggest blanket, right? In which all other blankets are part of. So you maintain your local deformation. It's like, I mean, how to say it? I mean, I hope you can understand that
Small
if you have
territory of
blanket,
blanket.
if I have a big blanket and if I have multiple marbles, all will dent locally, right?
Yes, sir.
So the dent will move along with the marble. No? As marble will travel, the dent will also move together.
Yes, sir. Like if we
Understood?
keep a heavy object at the center of the blanket, it will like go down even more.
Yeah, correct. And the lighter one will create a small dent,
Yes, sir.
but eventually the lighter will move towards the bigger one, isn't it?
Yes, sir.
So that is how Einstein defined the gravity. He said the gravity is a kind of a space-time curve, and the space-time curve will let you fall towards the bigger, heavier one. Understood?
Yes, sir.
So that imagination, okay, of course, I will not bring into the JEE learning. So this is how you can create some intuition that everything is trapped in a blanket. What I'm saying is the biggest curvature will follow. You will follow the biggest curvature. So what is escape? Escape means I give you sufficient velocity not to return back to the same blanket. Rather, you become part of some other powerful blanket. Understood?
Yes, sir.
So anyway, what I'm trying to say is case two. So much. So don't go much deep into all this because this is not required for GE. But of course, later on you should search about the space-time curve, the general theory of relativity. That's called the general theory of relativity. So that's a different way of looking at the gravity. Like the way here we look at gravity is simply force, and the way there we look at gravity is like a trap. So everything is trapped within something heavier because every heavy object creates a bigger trench compared to the lighter one. So let's say black hole is created the biggest trench. So it is said that the sun is moving around some galaxy. So the entire solar system is moving around the galaxy. So when I say you go home and you come back, do you come back to the same place or different place in space?
A different place.
In fact, we all are, even there are twins born with a fraction of second difference, they are not born at the same coordinate. Now imagine how interesting is this. We all born in different space coordinate, although it may have the relative address same. And when you go to, let's say, washroom and come back, you're not at the same coordinate in this space, isn't it?
Yes, sir.
So we don't have luxury to trace the same point.
Yes, sir.
Yeah. So every person ever born on this earth, they have been born at different space coordinate. Okay. And
Yes,
when you were
sir.
born, yeah, if you when you were born, then you must have interacted with the space cosmic radiation. And this cosmic radiation creates some sort of mutation in the brain during the birth before the prenatal stage. And that's how miracle happens, that someone is really extraordinary genius like Einstein. So they're not born, the god is like having the predefined pattern that, okay, I'll give you one genius per 100 years, that's sufficient. Imagine Newton changed so much, Einstein changed so much about science that we now are left with no more changes. So
Yes,
for
sir.
last 200 years, we haven't really developed something extraordinary. Understood? So
So
now
not
the world
even
is,
like at the molecular level, people do research.
nothing is left for the research, because now the cost of research at a level that we need now is too much for the country to afford. So now everyone is avoiding those research. So the next level research is called the string theory, the high energy physics. But the cost of entering the nuclear, you can say, see, we have entered the nucleus easily, because we know how much energy required to break the nucleus for the fusion reaction. Okay. But when you break the nucleus by so much energy, so much investment, you come to the particle proton. So now the next stage is entering the proton and seeing what it is composed of. So we have gone to that level also, and we have now called the something called the God particle, okay, the Higgs bosons. But now going further inside is now becoming challenging, because as you go deeper, the energy becomes extraordinary, and to attain that energy is really really difficult. And even if you attain the energy, providing that energy to that small region will break the law of physics. Understood?
Yes, sir.
So Einstein said that every development now which will happen, and he said in 1900 only. So almost 120 years has passed. He said in 1902. So after 120 years, what he said that time, that every development now will be only in the sixth place of decimal. It means the real life will not change. What will change is the beyond that position, the sixth position of decimal. So now, because science is not having much to discover, we are moving towards a discovery rather than application based discovery, that how to use the discovery that we have already made. So now we are moving towards the inventions. Okay. Discovery is over. Breakthroughs are almost over. Now we are towards the inventions. Like we create something which can be useful for the human being, the next generation. So science is progressing at a very fast pace. And even after, I think maybe after 100 years, the Elon Musk idea is actually very much there. We have to escape the planet to find the survival on the other planets. So we have to design the way that we can survive on Mars also, and maybe we have to start kind of attacking the other planets, and we have to become aliens.
This alien invasion.
Yeah. Okay, don't worry. These things will happen in the next 5,000 years. But anyway, okay, explore. But anyway, what I'm saying is, if v equals to v naught, the path will be circular orbit. So you will never fall back on Earth. So never fall back on Earth. What is case 3? If you throw with a speed which is more than orbital but less than escape, that's interesting. So in this case, I'll do the small Earth, so that because I know the velocity is very high. if you throw something like this, at a very high speed, okay, and I say v is more, then it will follow the, like, again the next path will be elliptical, and this will be the nearest point. So the Earth center will act as the focus, but this will be the nearest point. So H plus RE is the foci.
Like a similar situation like how the solar system now.
Yeah. Correct. So here the H plus RE is basically A1 minus E, right?
Yes.
So I need to know the eccentricity of this plane, I mean this ellipse. So if they mention the eccentricity of this ellipse, I can say that the H plus RE is this much. Okay. And then okay, you have, because this is the regular question of elliptical motion, so you can think in that way. And if question comes, you can actually attempt. It's not very difficult. Understand?
Yes.
This is like a R minimum, and this is the uh, uh, perigee. Oh, yeah, that's fine. The nearest point is to perigee, right? Perihelion. We call it perihelion, but okay, we call it the perigee, the separation. So perigee is equals to H plus R. This is called perigee. This part is called perigee. To be technically correct, and whatever you project will move in this elliptical path. Okay.
Yes.
So okay. So let's say if you want to find the again time period. So this is the case like we already have a satellite moving around the Earth. Okay. Now imagine a comet comes and hits the satellite. Technically, it will just burn there only. But anyway, let's say it's not burning. So if you kick it, let's say if a meteorite is coming this direction, a powerful meteorite, and it makes a hit like this. So it will be moving in a big circle, right? Like big. Now it will be, and let's say you attain some velocity. So because of the impact, the velocity of the planet will increase, right?
Yes.
And if the velocity of the planet will increase, then you cannot follow your the orbit path. So what will happen next? Then you have to
So,
check whether this velocity is more than escape or less than escape. So let's say
yes.
we can conserve the, let's say we conserve the momentum part at that location, and we will, after solving the conservation momentum and using the coefficient of restitution definition, we can find the velocity of the planet. And if we know the velocity of the planet, then we can guess whether it is escape value from that location or not. I mean, of course, the escape from that location will be less than from Earth, right? Because
Yes.
already you're away from that, so we now need less velocity for escaping part. So once we know that okay, this is sufficient for escape, it will follow the either parabolic or hyperbolic path. Parabolic means exactly equals to escape, and hyperbolic means beyond escape. So now the question is, what will happen if I throw something more than escape? So from Earth, if you throw something more than escape, it will land in a new orbit around the sun. But again, there is a condition. If that velocity exceeds much beyond the sun's gravity, we call it third cosmic velocity. It means the velocity which is sufficient to escape from the where?
Solar system.
Yeah, escape from the solar system. That's called the third cosmic velocity. And I think the value of third cosmic velocity is roughly 17 kilometers per second. If I can throw something from Earth at a speed of 17 km per second, it will leave the sun as well. Now, this is the last question of Eurodub. Actually, this is the last question of Eurodub, which talks about the approximate answer, which I will prove it. Don't worry. Anyway, I'll come to this later on. So, case 4. What is case 4?
Sorry, can you just
Case
come back in 10 minutes?
Yeah, fine. Okay, are you there? Hello, hello, hello. Hello, Hasika, are you there? Hello, 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 hello.
Sir,
Yeah.
sir, I just now came back, sir.
All right. So what is the case for?
So when the velocity exceeds escape velocity.
When it is equals to escape,
Yes, sir.
then path will be parabolic. And parabolic means you will leave the trajectory, you will leave the orbit of, you leave the gravitation of Earth, but you will follow the orbit of Earth itself. So the orbit of the planet becomes your orbit. Understood? And the case for case 1, if you exceed this, then hyperbole. And see, the hyperbola, parabola, these are some mathematical definitions which you have studied in the conic section. You will study about hyperbola soon.
Sir, hyperbola in the sense how will the object move, sir?
Again, hyperbolic means if you know the conic section, hyperbola is like this. You can draw in line something here. Something.
Yes, sir, but like I can't
So if you have a
exactly.
yeah, so if you have a cone, so a cut which is part of both the upper and lower cone. So you have to make a cut like this. I mean, just a minute. You make a cut like this. Difficult. Okay, anyway. Yeah. So when you cut from the top and bottom, then the part which will be cut will have a part here and a part here. Understood? So you cut two small parts from the both the shape actually. And because these two parts lies on the two different cone, so together we call it hyperbola. So hyperbole is a term which means beyond something. So the cut is beyond one cone, it goes to the two cones. So if you cut something here, it will become so this is again I think hyperbola. If you take the base and if you cut something using base, it becomes parabola. This is the parabola. Everything else is happening. Okay, and if you have the cut which is beyond this without touching the base, it's ellipse. And if you cut something like this, it's a circle. Understood?
Yes, sir.
So everything comes from the cone only. That's what we call conic section. Everything comes from there. Anyway.
If the orbit of the planet becomes the orbit, like orbit of the object itself, then Earth technically like doesn't it move in an ellipse?
No, then technically the planet, sorry, the object becomes the new planet moving around the sun. So they say this is the orbit of Earth. Okay.
So isn't it an ellipse?
Yeah, no, no. The Earth orbit we will take as yeah. If Earth orbit you take as ellipse, it's ellipse one. That's correct. So when we throw something with escape, we don't give sufficient velocity. We give, so let's say we have some object here. We launch with some velocity. then eventually after launch it will fall back to the same orbit. And now it will move around the sun. In fact, the Earth orbit is not like this ellipse. It is almost circular with eccentricity at the second place of decimal. So it is close to zero, no?
Yes.
But because of the dimension, this small e is also good enough to change the variety of things. Okay. So what happens that if you throw with something with escape velocity, it will leave the Earth orbit. So it will leave the Earth attraction and will follow the trajectory as described by the sun's gravity. So gravitation force of sun will decide everything. Understand?
Yes.
And it will follow the same orbit as the Earth is following. It will be slightly elliptical, that's correct. But we are talking about this trajectory. This trajectory will be in the frame of Earth. This trajectory will be hyperbola. That side. Okay. So you can think this. Anyway, so I'll come back to the concept which I was talking about. The first case. So right. So now I am designing a special orbit. So the planet was actually moving in this direction. With some velocity v naught. I don't know what is the velocity. The given quantities that we know, this height and this is equal. Both are equal. Oh, again, okay. Anyway, I assume this height. And why I said these are equal so that we can cut the ellipse into two halves. Okay. These are almost very much flat. Correct.
Yes.
Yeah. And to shift I hope you can understand this, right? So if I give r and r, if the height of the orbit, so initially it was this height. So the planet was moving with velocity v not in this orbit actually, like this. So we can say v orbital will be how much? We know the formula. The orbital velocity is gm by r,
Yes, sir.
and this is like okay, just a minute. Let me make it v only, so that I can relate something. So this we can write as v orbital by root 2.
Yes, sir.
Because gm by r is the v orbital of the Earth, which is like 8 kilometer per second, if you remember. Where I can say yeah, v naught is basically under root gm by re. Like close to the Earth, if something is orbiting the Earth near the Earth's surface, we write like this.
Yes, sir.
And this value is 8 kilometer per second. So anyway, this is the situation. This is the planet is moving in this orbit. What I'm trying to relate is, if I stop this planet, if I make the v 0, if I if v becomes 0, then how much time it will take to fall back on Earth.
So it will basically be covering 1/4 of this ellipse.
Yeah. So we are covering only one total ellipse.
So that means 1.4 by 4.
No, this is not 1.4. This is 1.4 is only for the near the Earth surface. If I'm moving like this here.
Okay.
So again, we can add if I make the time period as t, and see this is the focus. Okay.
Yes, sir.
So here things are not so good. The reason is, let me tell you, there is some problem. So earlier you were coming from top to this point, na, bottom, this point. Remember the sun example?
Yes, sir.
Yeah. So you were almost traveling half ellipse, right? And while traveling half ellipse, you also travel the half area also, right? But while traveling quarter ellipse, you don't travel quarter area. Do you realize this? Perhaps no. So this is the focus, almost here.
So like a little more than quarter.
Yeah. So now when you go from here till here, what is the area swept? So area swept is only this part, no?
Yes, sir.
And is this half part? No.
So it's more than.
Just so this is much more than half, isn't it?
Yes, sir.
And we know the time will be proportional to area swept. And that is how we have to think a bit more than normal to solve this question. So let me try this question. Even I haven't solved this before, but today we can solve. So we know that the semi-major axis is 2 RE. So we can say A is also RE.
Yes, sir.
So they need to give the B is roughly 0, which means E is close to 1. Sorry, B is A and A minus E square. So B is 0, so E is almost 1. Yeah, E is close to 1. Anyway, so I think for approximation part, we have to take this as half ellipse, right? This area, if I take this B, this is the A. So how much is this area? So it is pi AB by 4, the 1/4 of the ellipse, plus
Yes.
half AB, correct? Isn't it?
Yes, sir.
So this is basically, yeah, we got the answer. Now we know the area. That's easy, no? So that's this is the T. So T proportional to this area, correct?
Yes, sir.
And total time is proportional to pi AB.
Yes, sir.
So T by T is equals to pi by 4 plus 1 by 2. Ah, nice. That's it. Understood.
Yes, sir.
So time is how much? Time is T into pi by 4 plus 0.5. Oh, we
Yes,
got
sir.
the exact. So this answer is, okay, let me do pi by 4. Pi divided by 4
TB.
plus 0.5. It is 1.28. Just a moment. Pi AB. Upon pi, na? Upon pi. I missed the pi part.
Yes,
That's why
sir.
the mistake. So T turns out to be capital T into 1 by 4 plus 1 by 2 pi. That's the right answer. Yeah. So 1 by 4 is 0.25 plus 1 by 2 pi. Okay. 1 divided by 2 pi. What is this? 1. Ah, the mistake. Plus, it is roughly 4 point. This is actually 0.41 T. So it
What
is
is
definitely
T?
not. T is the total time period of the this time. The time period of the orbit. No. Sorry. Aha. This is the time period to fall down. This is the T. Time taken to go from top to the earth here.
This is in small t, but then capital T.
Yeah, we need to find the capital T is the total time period around the earth. Okay. Like for this ellipse, okay, just wait. I'll come to that. Anyway, okay, I made some mistake. This T is different. Yeah, this T is the time period of this full ellipse. To if it could make the round like this, this is the time period. Okay,
How
so
will we
let's say the
calculate?
yeah, just wait. So we can calculate the time period for this orbit. No? Let's call T dash, or let's call the time period of this is let's name it something TO. Time period for circular orbit. Like before the satellite fell back on the Earth, it must have some time period, right?
Yes, sir.
In its own orbit, isn't it?
Yes, sir. Sir, so these two cases can be related by Kepler's law.
Exactly. These two pieces we are going to relate by Kepler's law. So what we can write is that the time period of orbit is proportional to 2 RE whole cube. Okay. And the T is proportional to what?
A square or like RE square.
Uh, uh, oh my God. This is also because the semi major axis is how much here?
So here is RE for the ellipse.
Yeah, it's R. That's what I'm writing. T square. Like this, correct?
Yes, sir.
So here the semi major axis is RE only. So we can add this relation. So we know that T by T naught equals to 1 by 2 power 3 by, what is this? 3 by 2, correct. Which is 1 by 2 root 2. So T will be this upon 2 root 2. Therefore, the time taken will be how much? 0.41 T naught by 2 root 2. That's quite different answer, right?
Yes, sir.
So this kind of challenge, this is very challenging. I mean, this is Olympiad level problem. But this is how we can think about it. Understood?
Yes, sir.
Not very easy. As you can realize, this is not very easy, right?
Yes, sir.
Yeah. 0.4 factor will come. So of course, this is a very challenging problem, and very rarely we come across questions like this. But this is how you can think about it. Okay. I think the rest is something which you can solve from the textbook and try to finish before the next lecture so that we can discuss the doubt from the gravitation
So
and
the area of,
revise. Pardon?
sir, the area of problems 33, sir.
Yeah. Only Rhoda problem, because see, Rhoda problem is mostly about Kepler's law and these relation, the area relation, time period relation, and so on.
Yes.
And my notes is all about the electrostatics part, like the electrostatics equivalent of gravitation, and in fact both is there. So try to finish the notes also so that you can have a good grasp over the both concept, and then we can then practice from your for Kepler's law part. Okay.
Okay, sir.
All right. So this I will now assume as end of the gravitation, and few concepts which I wanted to discuss I discussed today. And okay, what else I can say? Yeah, only you practice, and if you have doubts, then only I will explain some new concept if required. Okay.
Yes, sir.
Keep in mind that most of the cases the center of the earth will be the focus in elliptical path. Also keep in mind that the question will require conservation of angular momentum and the energy to solve both the concept. And in some situation you can take care of the the radius of curvature concept to again solve. Okay.
Okay, sir.
All right. So let's end this chapter. So I will just write the end. Okay. So what will start next lecture? We are going to start the current and electricity.
Capacitance.
After that,
Oh, okay, sir.
if you want, I can start capacitor also. But yeah, I'll start capacitor. That's not an issue. I think you can understand. If something is required, I hope that you have a basic idea about what is current, what is V equals to IR, Ohm's law. Okay.
Sir, in NCERT, I think capacitors came first and then corrected electricity went on.
I know. Because the concept of RC circuit is in current chapter, right?
Yes, sir.
And most of the RC circuit problems are the JEE problems. That's why the RC circuit we cover in capacitor. That's why I teach later on. So in a way, it's the same thing. I mean, okay, leave it. Don't worry. Everything will be covered. All right.
Okay, sir.
Okay, bye and take care.
Bye, sir. Thank you, sir.
Okay, I would like to change one time. The Thursday is really difficult for me to manage. So we can shift the Thursday either on Friday or Saturday.
Okay, sir.
Not on Saturday, Friday or Sunday. That's only 2 days.
Sir,
Either.
Sunday evening I'll be having class
So
and
Friday,
Friday evening also. So Friday
Friday
morning,
also.
sir.
Friday morning. Okay, I will try it in Friday morning. That's it.
Okay, sir. Thank you, sir.